So we discussed about LangChain in good details in last few weeks. Now we want to move a little ahead and want to get into the actual topics rather than just some technical stuff. So one important topic which all of you would have at least heard of, if not used by now, would be RAG. So how many of you have heard at least about RAG? What is RAG?
So it will give the response based upon the documents or based upon the it will strictly stick to the content which we provided.
Okay.
It don't hallucinate.
Okay. So don't hallucinate. If you're using an LLM, there's no possibility that there will not be any hallucination, right? But at least you could give a relatively better context window, right? And considering how you write your prompts, there's a good chance that it will only answer from that data set that you have provided. But if there's an LLM, never assume there's no hallucination. Okay. Anyone else? Anyone heard about RAG or used it by now?
So
Yeah, in the
RAG
last,
in a
yeah, Saurabh,
yeah,
please
Sachin.
continue.
Okay. So RAG in a simple term, if we say, it's like a what is it? Like an open book exam, we can say. So basically,
Hmm.
uh, if just like example, if we give, if we are developing like a chatbot or something, and if we want to just give a answer in a certain context, so we set a predefined rule or predefined data set where it uh, throughout the process it retrieve argument and generate the output as per the rules or the protocol we set for them.
Okay. Not a bad explanation at all. Uh, okay. Let me try to give my view. All right. So I think someone else is joined as well. Okay. So today, whatever we build, right, everything is moving directly or indirectly towards RAG. All right. So in every software application that we are building with AI, and in one form or the other, it is looking at a certain data set before answering. I'm only talking about the application which are being built for some organizations. Okay. RAG in general stands for retrieval augmented generation. Okay. So in simple words, you can say first retrieve relevant information. Okay. And then give that information to your LLM call and only then answer or only then generate the answer, so that you are looking at the right context, not everything that the model or an LLM would have been trained, because LLMs are trained on complete internet data. All right. But there's a starting point to learning or thinking about RAG. So we are going to discuss that, and the next session we'll reach to RAG exactly. Okay. So let me just start sharing my screen and then we'll discuss. Let me know once my screen is visible.
Yes.
Yes, we can see yours.
Okay. And you're able to see the PPT?
Yes, embedding plus vector databases.
Okay, cool. So we are going to discuss about embeddings and vector databases. All these searches that we do, all right, there is a methodology to how you search. We cannot assume that a model understands some words. So for us to get better results, right, we need to give it embeddings, which it directly internally creates. But for a RAG application, whenever we'll create, we'll need to propose with one or the other form, maybe with a vector database, maybe with FAISS. Depends on what kind of solution, what kind of problem statement we have at our end. Okay. All right. So first thing is the problem statement. All right. So now look at this. User asks affordable meals in Pune. If you look at general search, what it will do? It will start looking for the exact words. Affordable meals Pune. All right. But do you think Google search also works like that? If you search for word affordable, will Google only give you the answers that are using the exact word affordable?
No.
It will also include these words: cheap, you know, cheap food near Pune. Would cheap food near Pune still mean affordable meals in Pune? Budget restaurant in Hinjewadi could also be a good search result for affordable meals in Pune, as well as pocket-friendly thali places, right? So
Yeah.
this is if you're searching with keywords, right, or any search solution that is being built upon only on keywords, right, that comes with big limitation that you will not be able to get results when the keywords are different, though their meaning could still be same or similar. Hence search. Okay, what does semantic mean? Semantic in general just means meaning. All right, so whenever you'll think about or hear this word semantic anywhere in from NLP perspective, from AI perspective, instead of getting confused, just think about the word's meaning. The word in itself means meaning. So if we are saying semantic search, indirectly what we are saying, there's a system that understand the context behind it, okay, or the meaning behind the keyword, and based on that definition or understanding, now we are searching, hence semantic search. Okay, it does not only focus on exact words, it tries to understand the intent or meaning, right, as I said. Now look at this. If you're searching with affordable meals in Pune in Google, if you search, it will check what all blogs, what all Zomato comments, etc., etc., on internet are available, which semantically are similar to this, and based on this, will provide you an output. Okay, but tell me this: how does it know that affordable and cheap and pocket friendly or budget means similar things?
Embeddings.
Yes, embeddings. That's the same concept that we learned in, I think, a second or third class when we were discussing about LLM, right? Remember embeddings we discussed?
Yeah.
Yes, yes, sir.
Yes. For LLM, the first thing that happens is the input text is gets converted into tokens. Then those tokens are converted into vector form or embeddings. Okay. All right. So, but what is an embedding?
Numbers, like number
Yeah, numerical
systems.
representation.
Okay. And why do we need to do that?
Machines don't understand text.
Yes, a simple one line explanation, right? So machine or computers cannot directly understand language like us humans do, right? They only understand binary or numbers, which is 0, 1, or in some numerical form, all right? So what embeddings does is it converts human language numbers so that machine can compare meaning mathematically, all right? Now, an embedding actually converts text into a list of numbers. All right. Here, I love biryani is a list of how many numbers? 384 numbers. Okay. So basically, there are 384 things or ways that computer has understood or learned one or the other aspect about this English sentence. Okay. Now, I'm pretty sure one question which would come in your mind is, what does these each number mean? Can you define these numbers on your own?
No.
It's like the
No.
position, like in the embedding space, the position where the text is.
But is it understandable by us or not? Humans or not?
No. No.
No, I guess.
No, because these are something
Yeah.
which are learned by system and we don't have visibility on that.
Absolutely. So whichever model which was built for embeddings that has learned it during its training, right? So the machine has learned it and kept those numbers for itself to understand meaning of every word through which it creates every sentence. All right. So we do not understand those uh, numbers exactly, but we do know that in a vector space or a numerical space of n number of dimensions, here we are saying 384, there are 384 dimensions. Those words which are semantically similar would be very near to each other. Okay, that's the only thing which we need to understand. All right. Now, if you just look at this and this, you'll realize something. We have three sentences. I love biryani. Biryani is my favorite, and Python is a language. All right. Now, and this is again just an example, right? The real numbers could be little different. These came from OpenAI embeddings so that we know because the input is provided by us. All right. So it's 0.82, 0.80, and minus 0.31, and then minus 0.14, minus 0.12, and 0.67. So if you now look at those numbers, even though we do not understand from how or from where did these numbers came from, or how have the machine learned about it, or different dimensions, but if we just look at the numbers, we would be able to realize that 0.82 is much near to 0.80 rather than minus 0.31. Yes or no?
Yes.
Yes. So that's how machine is knowing that I love biryani is near to biryani is my favorite. Okay. So that's what it is. Similar meaning is nearby numbers, and different meanings is far apart numbers. And that is how the machine would understand. Okay. Vector space, as we discussed about it as well. First of all, what is a vector? If anyone is still confused about it, and whoever is confused, right, I would like you please to speak up. If you know something, great. If you don't know, please speak up. What is a vector?
Just a list, like only
Just a list of numbers,
numbers. Yeah.
right? Yeah. So vector, we just call it a list of numbers. So when we say vector space, what we basically mean is a space where these embedding numbers lists placed, all right, or indexed. So because whenever you think about a list, the first thing that comes in your mind is index. So you can consider that. But what is happening is where in the embedding a number is listed or placed. Okay. Think of so this is one example, but let's think of something which we use regularly. We all use Google Maps, yes or
Mhm.
no?
Yes.
Yeah.
Yes.
Okay. So if you know, just, try to squeeze it a lot, you'll see whole of the world, right? And then you keep going on certain thing, you put some direction, and the 2 points that it would show, you would be able to get the right distance. And based on those 2 points, which are, in the real world, those distances could be far apart, but it would still be able to tell you that any 2 points which on a map looks closer are in real world as well closer. And if a third point you erect, which is farther from those 2 points, in the real world, when you travel, you'll realize that yes, in real world as well, it is farther. So that is just for our understanding. Or create a map in your mind, right? That vector space is almost like a map where you can see if something is near, something is far. If you remember during the LLM session itself, I showed you one projection. I'll now ask all of you yourself to just go and check that. Okay, I've put the link on the chat. All right, if you put any word in here, in the right side of it, you would see a place to put in word. If you put a word, you'll see the map giving, related and nearby words to you, with which you can understand that, which words are near to it for certain embedding. Okay, so that is vector space. All right. Again, as we said, we cannot visualize these 384 dimensions, but the math works same as a 2D distance on a map. All right. Okay. Next, I don't know many of you worked with it or heard about it, but at least as a concept, at least you should understand. Okay. So, but anyone if already understand, great. So can anyone tell me what is your understanding of cosine similarity? And then I'll give you one perspective, which is actually from interviews perspective, because people just want to know how do you understand things.
It is like the measure of how similar the words are. Like one means very similar, like less than five means like dissimilar.
Okay, cool. Makes sense. As we are saying here as well, right? If you like taking probability from 0 to 1, all right? If you get 1, that means you're talking about the same word, right? Which is 100% match. If you are at zero point 0.7 to zero point 0.9, you are pretty much at a similar level. And zero point 0.0 to zero point 0.3 means unrelated words, or words which have no relation with each other. Okay. Now, this is one of the hundreds of topics which sometime if the interviewer is sitting there want to make sure that at least from concept perspective you have gone through things, or you have at least heard these terminology and you would be able to make sense of it. So if as an interviewer I ask you Okay, you do tell me, that from numbers perspective, this is how cosine similarity is. But from vector space perspective, how do you calculate it? Can I calculate it with, by mathematically, can I calculate? I can say yes, right? But these numbers have reached to us with some calculations. So the right answer could be these are the angles. Okay, if the same link that I provided to you, if you'll open that link, right, you'll see XY measure given to you. Someone else is joining. Okay. Okay, at least tell me, did you actually open that link? Are you able to see something in that link? I'm not doing it willingly because, last time I did it and I hope that everyone understood, but some of you wouldn't have tried it. So if you try it on your own, that's little better than I explaining again.
Yeah, sort of tried it.
Okay. So you would see a blob of, so many data points, which are actually words. And the nearer dots are near to each other, and the farther ones are in real world as well relationally are different words. So if suppose, look at this, right? I have king here, queen here, right? The, and, suppose there's an anchor with which you are trying to calculate how far these words are, right? So suppose throne, okay? So if throne is your anchor here, king is here, queen is here, the angle would tell you the similarity. And that's how you can consider your cosine similarity. If the angle is wider, that means the words are far apart. If the angle is smaller, that means the word are comparatively near. Okay. More than that, you don't need to understand from concept perspective, ideally from usage perspective, identical is, these mathematical numbers is more than enough for you. Okay. All right. Next is embedding models. So there are two options available for us to use in the real world: sentence transformers and OpenAI embedding. The only difference, as you can see, sentence transformers is free for us. OpenAI embeddings is paid. All right. Now, who has worked with OpenAI embeddings from this class and who has worked with sentence transformers? And if you have not worked with either, that's totally fine. That's why we are in this class. But if you have, can you tell me what use case was it on which you use sentence transformer and for which use case you use OpenAI embedding?
So basically, I want to get the context of my source code repo. I used to open AI embeddings there, sort of, yeah, just to search
Okay.
something
All right.
through my code, basically.
Okay. Uh, is it your personal solution or
Yeah,
your
personal.
personal
Personal.
project? Okay. Okay. All right. Any reason that you didn't try sentence transformer?
No, I'm hearing this for the first time, basically. I did tried something on the Hugging Face mode, but Central Transformer is the first time I'm hearing.
Okay. All right.
Yeah.
No worries. So see, ideally we all start with sentence transformers. There's some positives and negatives to it. Positive is free. All right. Everything is there in your machine. The problem is this. It requires PyTorch, which is a 2 GB download. And because it is transformers based, so the older machines which do not have GPU, all right, this would be very slow, or pretty much the machine will not be able to take that load, right? So if any one of you have a very old machine, I would suggest you will go with OpenAI embeddings. So that's what, the code that I'll share with all of you would have commented code for OpenAI embeddings. If you are not able to download PyTorch or your machine is very slow, you can just comment the sentence transformers part of the code and you can uncomment the OpenAI embedding codes, right? And the rest of the key and everything you have already worked with, it would be same. Just in give your environment file with your OpenAI key, or keep it wherever is your workspace. Okay. Now the benefits of each is this runs locally on your machine, no API key needed. The dimensions are 384 per vector. For our use cases, like way more than enough. But if you want to have, a use case where the expectation is you need to understand much more depth, every word in much more depth, then you'll need more dimensions. If you need more dimensions, then go to OpenAI embeddings 1536. Okay. Again, this is on your machine, free forever. This is it's so called cheap, but see, everything that is not free, you can consider like they just keeps on adding on your cost. But still, the cost is not very high, 0.01 per thousand texts. Okay. Good thing about it is you don't have to download anything. And again, simple LLM calls as we have been making with OpenAI till now. And again, works on any machine that is connected to internet. All right. So one nugget which I can give is for the older solutions that we had, which are built on machine learning, and more specifically, whatever we are feeding to model way before that, whatever transformations we are doing to the input, right? There we use sentence transformers. All right. Now all the Gen AI solutions that we are building, if it at all comes to it that we have to do any embeddings, again that's also become little rarer because we are directly dealing with models. We input, we are not fiddling it with, we are just giving it prompts and expecting some answers in the format that we want. But if at all, so then the one or two solutions are using OpenAI embeddings, and again from corporate or enterprise perspective, the cost is not that high. Okay. All right. Next topic, FAISS or fast local vector search. Anyone heard about FAISS or fast local vector search before? So basically, fast local vector search is what we are doing, right? FAISS is the name of it because I think it comes from Facebook when it was Facebook, or now it's Meta, right? So Facebook AI similarity search, that's why it's called FAISS. But it is basically, if on at your local you're doing any vector search or indexing data, you can use FAISS. But again, just know this before even moving to that. FAISS is now only used when you're doing the POC. In the real world, not not something which I would prefer. Okay, if you're creating something which is going to be more than just a POC within your organization, go for some vector database rather than FAISS. FAISS is used just for local search. Okay, so now what is the use, right? So once you have embeddings, you've created all the embeddings. Now you need to search them. Now suppose this from RAG's perspective, if you are a large organization, okay. In fact, I think it would help, right? Let's take one person. Okay, Itisha, hello.
Yeah, Saurav, hi.
Okay, hi. So from your organization, can you give one example where you guys are actually building something with AI? Doesn't have to be RAG, just anything that you're building with AI. If you're at least aware. If not, then we'll, go to some other topic.
Mm, Not as such specific with AI, but yeah, the company wants something to be built with respect to Jira. I mean, anything that can be, any functionality that can be handled on Jira. So the people are thinking, I mean, still thinking at what can be done, how better we can use Claude. They just want to make something
Okay.
with, yeah.
All right. So with Jira, obviously there are a lot of things that people do and have already done with integrations, and Jira is coming up with its own AI capabilities so that the integration is not needed at all, right? But suppose this, right? If in Jira you would have so many projects, all right?
Yeah.
You would be working in one, there would be hundreds of different projects people would be working in. Now, for all the projects, I ask you that, I need to know which projects are doing good, which projects are not. And on that basis, can we project how much delay we have seen in the last year from the initial estimates of any project that would have started, right? So what we have to do is we have to, download a lot. Say for each project, you can get an export, or you have to export the complete DB wherever you are hosting it. If you're using what cloud one, then you have to ask the provider for the complete data. All right, you'll get a very large data set for
Mm-hmm.
them. Now you have to search within it. Okay, so suppose if you have a very large set of data, all right, and now you have to search in that chunk. So suppose if it's 10,000 document, right, and all those now from NLP or AI perspective or Gen AI perspective, we have started calling them chunks, right? A large chunk of data. So if you have 10,000 documents, suppose, now you can not compare every vector one by one, right? you have to do something so that it would be much faster. All right. For the same, FAISS comes in. Okay. As we said, it was created by Facebook, and it comes as a library specially designed for very fast vector search. Okay. And FAISS creates something called index. Index, I'm pretty sure we would know, but still, uh, you can consider index like your indexes in RDBMS, or if you don't want to go towards database at all, you can look at any of your child's notebook or your own younger days notebooks where you will see the first page would have index, right? So that is super optimized structure, search structure, or you can say lookup system that you have built for yourself, using which you would be able to find the nearest vector. Okay, so that is what FAISS builds and uses to search. Okay, and the flow is simple. First, create the index, then add all the embedding vectors into it. So you create an index, say, or a key to retrieve, and then you put all the values. Okay, and then you finally query it to find the top k or top nearest or most similar vectors. All right. So creating an index, adding all your embedding vectors, and finally querying to find out which are the nearest one. All right. That is how the search would work. And it is very fast for prototypes and all. Again, for POCs and all, a lot of people do use it. What is the limitation of FAISS? The limitation of FAISS is not great for metadata filtering. Basically, what it does is, if you talk about other vector DBs, they will not only keep vectors, but if there is some relative information, they'll keep that as well. FAISS only keeps vectors or the numbers. It does not store the original text or metadata. So what we have to do is we have to maintain a separate list for us that could tie us back to the actual word or sentence for which the embedding is created. So it will only be keeping an embedding, and when you search, it will give back the embedding. Suppose it gives you a number saying 1.0, comma 2.0, comma 3.1, whatever it is, right? Now you don't know what that number is, so you have to keep a separate list which can take you back to the original sentence or original word. So that's a uh, problem with FAISS, right? Or its limitation. And again, uh, FAISS indexes lives only in current memory. Once you close the program or stop running it, the data would disappear. And if you want to save it, you have to save it manually for it to pick it when the program restarts the next time. Okay. But again, if you're just starting with it, or just starting with vector searches, FAISS is enough for you to, do your POCs. But that doesn't mean that we are not going to talk about vector database. Okay, which would be part two. All right, I'll just give you on high level what this is, but we'll decide while we do the coding part, can we cover both the parts or not. If we can't, then we'll take the part two in the next session. Okay, part two, we are only going to discuss about vector DB. Okay, so what is a vector DB?
A database that stores vectors.
Yes, no genius needed here, right? So we talked about FAISS, right? FAISS gave us a fast vector search, but it still behaved mostly like a low-level vector engine. We have to manually manage text. We have to manually keep our metadata, right? We have to manually keep a list so which can connect or map your embeddings to the actual text, right? But any vector DB, we are going to take an example of Chroma DB. Okay, so this would be little different from it. It is a full vector database, and it is built specifically for embeddings and semantic search. Okay. I'm pretty sure that because Varun is from WK, I can ask this question. Varun, have you used FAB till now?
No, not yet.
Okay. In FAB, you would at least know that at some point we all have to use it, right?
Right, yeah, yeah.
Yeah. So in FAB, they have already created their own version of vector DB,
Yeah.
right? Which is again a
Mhm.
service taken from, I think, AWS.
Right.
All right. So that is, they call it Fab Index. All right. So it is again the same thing. They're using it as the same thing
Yeah.
as a vector DB, keeping or storing data as chunks. All right. All right. Coming back to the topic. So now one thing, right? for many people who just start with it do get confused because most of the databases that we worked with are relational databases, right? For an example, SQL. How do we search in SQL? Anita, can you tell me how do we search in SQL? Anita, you're there? Okay. Verson, can you tell me how do we search in SQL database or any relational database?
Using like queries, SQL queries.
Okay. But what do we search for? We search for rows of data.
We can search for the whole rows, or you can just search for the particular column.
Yeah, but mostly when you do select star from, select
Yeah,
top two
it's whole row.
from,
Yeah,
whatever, we are mostly searching for a row of data,
yeah.
right? What do we use for it? We use IDs, right? To reach to the right row. We use exact words, right? But in a vector DB, instead of searching for rows, all right, we search for semantic meaning. And how do we do that? With the embeddings that are there. Okay. So if you take an example of ChromaDB, we store everything together in one place. The original text, the embeddings, metadata, everything is kept at the same place. Like in FAISS, we had to keep a separate list to connect. We don't have to do it here. It is all there in the same DB. Okay. So metadata, if someone is confused about what is metadata means data about data or more information about your data. All right. For our RAG use cases, you can say more information about the documents being used. So you can say something like this: category is food, source equal to PDF name, whatever PDFs you're using, and then if there is specific sentence, on which page number does it reside? So say page number 12, page number 13, etc. Then year, right? So whatever information that you can provide about the documents or the text which you are going to search on, that is your metadata. Okay. And metadata is very useful because with it we can filter our searches. For an example, we can say search only food documents. All right. So only when we have already defined a metadata that says there's a category or this document falls in the category food, only then we'll be able to search for food documents. If you've not kept it, you will not be able to search it. All right. All right. One more feature is persistence. What do we mean by persistence? ChromaDB can save data to disk. So when the application restarts, your vectors and documents are still available. It is not in your runtime memory like it's in FAISS. Okay. So that makes it more practical for the real world RAG application. So just to remember both, FAISS is super fast vector search. ChromaDB is your full vector database for the actual production systems. All right. I'll give you like 4 or 5 most commonly used ones, but I'll tell you what, right? Now what is happening is most of the organizations, instead of going to these databases, which you can, some you get from different open source uh, applications, some you get from Hugging Face as well. But what I would suggest is now learn more about the directly provided by your cloud provider as services, because most of the organization relying on that, and in our organization as well, we are relying on whatever service is directly provided by the cloud provider. Similarly, I'm assuming most of the people are doing like that, because anyways you're taking your LLMs from there, and then pretty much everything that you're doing, all the solution that you're building are being built on cloud. So it's better to use those their services as well, rather than going for a third party or third thing, right? But again, I'll still give you some popular open source one which you can use. All right. Last, why this matters. So if you look at it, everything today is a building block, not for this only, right? For the RAG, right? Load document is what we are doing, right? Now splitting into chunks is what we'll do later. Then we'll have to embed those chunks, which we are doing, which we'll see how to embed those chunks, right? Then someone just message something. Okay, sure. Then we have to store in our vector DB, which we'll try today itself if given time. Okay. Last is we have to query that database to get answers. Okay. In the next week, we will add these details. Loading we can do today as well if the time permits, but splitting into chunks and then generating the answers we'll do in the next session. Okay. All right. So from this session, right, these would be the interview questions that could be answers, and those are real world interview questions which are asked. Some of them, like embedding, is definitely everyone asks, even I ask. And just to check if people have worked on some POCs or on the real world thing, we do ask about if they know about FAISS. That means that they have worked on POCs. But if they say that they have built a production system on FAISS, that's where how we catch that. Okay, this person might not have actually worked on any productionized application, but have done POCs, which is not bad. But if you're looking for someone with more experience, then you'd expect them to have worked on some vector DB. Okay, all right. Okay, should we take a 5-minute break and then start with coding exercise, or you all are ready to go for the coding exercise?
We can continue.
Okay, all right. Let me. But at some point we'll need a break, right? I'll need to drink some water, but we'll do like 10-15 minutes and then we'll start. Okay. Okay, I'll reshare my screen with now the coding part. I'll just share my VS Code. Okay. Let me know once the screen is visible.
Yes, visible.
Okay. All right. So we are going to build semantic search, or we are going to do the semantic search with our embeddings today. Okay. So first thing that we need to do is, which library did we talk about today? Sentence transformers. Okay. So we are going to use sentence transformers. All right. And which model? We also talked about the model mini LM
Um,
L6V2. Okay. So sentence transformer, as I already explained, this is the library that we are going to use. All right. And this provides you with an embedding model which you can have in your local. All right. It downloads the model once and then you can run it locally on your own PC. You don't need OpenAI or anything for that. All right. Now all mini LML6V2. All right. That is a very popular lightweight embedding model. It would convert all your text into a list of exactly 384 numbers, right? Or you can call it a vector of 384 dimensions. And it is fast enough, small enough that it can run on your
on your
laptop,
laptop.
and fast enough that you can actually, I think someone,
Saurav, actually, I have a small question. So it is always
yes,
384 exactly in all the,
no,
I mean, okay, yeah,
okay.
that's
So it depends on which model you're using.
okay,
Okay,
yeah,
so
right.
because we are using these are smaller models, so they are creating vectors or embeddings of smaller dimensions. But again, 384 is not a small dimension anyway. But as we saw, there are other models which much more dimensions.
Mhm.
For our purposes, 384 is more than enough. That gives the model enough understanding about words and sentences that it can find whatever is near to me, whatever is farther to me, etc. Okay, as we also saw in the PPT, right? The OpenAI one has more than 1500 dimensions. All right.
Yes, yes,
Does
okay.
it make it clear?
Yes, yes,
Okay.
Saurav,
So
thanks.
let's first try with a simple one, right? So let's do one sentence and embed it. So just a trial run. Okay. Now, how do you embed it? You have to do embedding equals to model and then encode it. Okay. So that is how you will encode your text and create your embedding. All right. So now if we print it, yeah, this works. But what all things we can get? Okay. We can get type of it. All right. So we can say, all right, we can get type of it. We can look at the dimensions. For dimensions, we have to, how do you check length of any list? Because the dimensions are a list, right? The embeddings that is generated is a list. Yes. So if I want to look at the dimensions, what I'll do is I'll do length on embeddings. Okay. All right. Let's run it. And by the way, you can run it on your local as well. It might take a few extra seconds because you're running a model on your local. I'm sharing it with you. You can run it on your local as well. So because this is the first request, it will take little more, a few more extra seconds. All right. So this is just a trial run. Now look at the type. It generates a numpy array. Okay. And how many dimensions does it have? 384. All right. So this was the one sentence which we embedded. All right. Now what we can do is we can look at more sentences. All right. Now I'll give this as well, so you all can, just follow me and keep running. All right. Look at these sentences. I love eating biryani. This is related to food. Again, this is just a comment, right? We have not yet updated our metadata. Now, biryani is my favorite Indian dish. Food. Virat Kohli scored a century. This is about cricket. India won the cricket match against Australia. This is about cricket. Python is a popular programming language. This is about tech. And I'm learning machine learning with Python. This is again about tech. Okay. So we have, more data to play with. Now, as we created earlier, we have to just create embedding. Okay. Now, if you see, we are using the same dot encode. Okay. So model dot encode, it will also accept a list of strings. So the earlier it was just a single string. Now a list of string, it does accept it. Okay. Now let's see. Yes. All right. And we can also get the shape. Yes. Okay. This, what does this give you? In the
First,
list, whatever is at the zeroth
Zeroth point.
index, right? Okay. And from our list, what would be at zeroth index?
I love eating biryani.
Yes, I'm assuming you do, right? Okay. Let's again wait for a few seconds. I'll give you this part as well. You can keep running, but keep running with me, right? So that you'll be able to follow along. I'll anyways give you. So this is, whatever we are doing live is a much, milder version of what I'll share with you so that you can go through more and understand more implementations, because within, a live class of 1 or 2 hours, it's not possible to write all that code and explain, but to give you a understanding of what we do, I think this is enough. Okay. All right. So batch encoded 6 sentences into 6 embeddings with 384 vectors. All right. So that is how you actually convert into embedding. All right. Next, what we have to look at, we can look at the cosine similarity. Okay. Again, remind me, what is cosine similarity?
Measure of how close the text is to each other.
The same thing, right? So basically, now you have created or converted into numbers. Now we need to check how similar those numbers are. Basically, how similar those numbers and hence the words from for which the numbers have been calculated are. Okay, so we'll go for cosine similarity. So this sklearn, which is one of the widely used, libraries for anyone working with ML. Okay, we are just using a small portion of it. sklearn is very wide. I have been teaching like data science specifically, not GenAI, but data science from so many years. 60% of it was from sklearn. All the models come from sklearn. All the machine learning models that you would have heard of, right? But anyways, we just need cosine similarity for us. It already provides you with, so we'll use cosine similarity. Okay. And it again, it comes pre-installed when you have sentence in transformers. All right. Now, what does cosine similarity take? Okay. Cosine similarity takes in an array of embeddings, which would have been created for us. Okay. And what does it return? It returns a matrix of score. That is every sentence compared with every other sentence. So comparison is already done for you. Cosine similarity. Okay. Now for us, one function call would compute all similarity scores at once. What we'll pass is, we'll pass our cross 384 embedding array. Okay. Now let's see. So just you have to call cosine similarity, and wherever you have kept your embeddings, just give that variable. Okay. Now how would it have worked, right? So it would be something like this. Sentence at list index 0, it will keep I love biryani, all right, and so on. So this is what you'll get as a complete matrix in one go. All right. Now just if you want to see it, how can we see it? Okay. So what we can do is we can print it one by one. Okay. What do we mean? Let's differentiate here so that we know where we are going. Okay. So there's some space in the output. That's it. Okay. Next is, you can say at a certain point in your matrix, which is, okay, what is at 0, 1, what is at 0, 2, what is at 0, 3. All right. This is for, so which are of same topic, 0, 1, 2, 3, and 4, 5. Yes. Okay. So if they are of same topic, will you get a lower score or higher score?
Higher.
Higher.
Okay. In fact, in the expecting higher scores. Okay. Now, which are like not related to each other. So 0 and 2 are not related to each other. Okay. And let's take two more. So 4. So we can take 1 or 4. Give me two more which you think are not related to each other. Is 0, 3 correct?
Yes.
Okay. Let's take 0, 5 for this. I'll give it to you as well, so you all can run at your side as well. I've pasted. Did I paste only that part? Wait. Yeah, I pasted in the Teams chat. Can you just check if you're able to see it?
Yes, Saurabh.
Okay.
Can you, control A everything and paste once? I'm getting some issue in import. Maybe some silly mistake I'm doing. Yeah. Thank you.
Okay. All right. So
Saurabh, it is saying that no module name for sentence transformer for me when I try to run the code.
that is because you have not installed it. You have to do pip install. Go to your terminal, do pip install. You'll get that model.
Okay, okay, thank you.
I already have that model, so that's why I don't have to. Okay, you do this pip install. Okay, whichever model you want, just this same,
Okay.
but do it in terminal. All right, so now look at the result. So which one did we compare, right? My scroller is not working properly today. Okay, I think we should have taken not these, right? These are not similar. 0, 1 was food, then 2 and 3 it should have been, right? So that's a mistake which we did. That's why we are getting lower score. 3 and then 4 and 5. Let's run again. You understood, right? What mistake we were comparing everything against the 0th index. I either miscopied or did something because of which. So 0, 1, 2, 3, 4, 5. Though these should be the values because these are the sentences we see are near 0 and 1, 2 and 3, 4 and 5. What I was doing is I was comparing 0 to 2, first 0 to 1, then 0 to 2, 0 to 3, which is why we were getting smaller values, right? So now it's much clear, right? So similarity between sentences 0 and 1 is this is a high score, right? Anything above 0.6 is a high score, all right? So this is a high score. These scores do look very small, so this gives you limitation of this model, all right? But they in real, if you see, they would be much nearer. But again, that is also on the comparison points. If you have more comparison points, the results might be little better. We have very limited data, all right? But the ones which are not similar, you can see the numbers are very small or the values are very small. So these numbers or these values kept at those indexes of the list is definitely different. All right, make sense? Yes or no?
Yeah.
Yeah.
Okay. All right. Next, we'll go to FAISS, which is Facebook, and we are going to use it for fast vector search. Okay. So again, these lines I'm keeping so that in the print it's very easy for us to understand. So that's the only reason. Otherwise, they serve no purpose. But I'm pretty sure this is already clear to everyone. Okay. Now, which library do we need? FAISS. Okay. And because the output we'll get from it would be in numpy array. Hence, we'll take numpy as np. All right. So these are the two libraries which are needed and which would be able to do our job. Okay. Now let's look at the larger data set. All right. This time we have taken, so this is our knowledge or database that has values of Hyderabadi biryani uses blah blah blah, Mumbai vada pav uses blah blah blah, dosa. So again, if you look at the right side, this was just to explain you how near or far they are. So first three talks about food, all right. Third and fourth talks about cricket. 5 and 6 talk about tech. 7 and 8 talk about travel, and ninth one talks about education. Okay, so you have these values that would be talking about more set of sentences. Now what we have to do is we have to embed these sentences. Okay, now earlier we were embedding, and then now we'll embed for to be able to search with FAISS. Now one thing about FAISS is it specifically requires float 32 value. Okay, so whatever value, whatever encoding we'll do, we'll put as type as float32. So that is by default converted to float32. Okay. So, okay. So this is this, but it's better to be sure that our type is float32. Okay. Again, because FAISS requires float32 specifically. All right. And what is 32? That is the 32 bits per number. Okay. Anyways, like our sentence transformers would return float32 by default, but just to avoid bugs if possible, we specify it as well. Okay. Now, just to look at the how it has created it, right? The embeddings, how do they look? Let's run it and see. I'll give you this part as well. Again, if you do not have these libraries, you will get error. So what you can do is you can do pip install and the library. Okay. Anyways, the files that I've given you already has pip install as comment, or will I, you can get it from Google Drive. So you just have to uncomment those and run. Okay. Happen it didn't. Because I've not printed anything. Is it? Do you see? Have you printed anything?
No.
No.
No. We have just given it shape, right? So if we print it, we'll get it. But if we have wanted to print it, let's go a little ahead, right? The next thing, let's do it so that we'll print it all together. Okay. Okay. Next is the thing that I told you, right? What we have to do? We have to create an index, create a FAISS or FAISS index. All right. Now there are few things about FAISS index. There are multiple ways that you create FAISS index. You can have flat. You can have there are different Roman numbers like 4, 5, 6, etc. So you can have 4F flat or IVF flat, right? Or you can have HNSW flat. All right. Or sorry, HNSW, not flat. Right. There is difference in those how they function internally. The one that we are using is flat L2. Now why? Okay. Flat L2 is the simplest of index. Now because we have very less data, right? This is like negligible. So flat L2 works. Okay. Now how does it work? It basically means it stores every vector exactly as is and compares your query against every stored vector one by one, right? So it is going to compare first with 0th index, then 2, then 3, then 4, then 5, then 6, right? Because we have very less data, that's okay, right? But if we would have very large set of data, this process would be very slow, right? It is pretty much like searching. I don't know how many of you remember there used to be phone books earlier, right? So if you're searching in a phone book by reading every single entry that, right? So and this L2 specifically, right? So flat means flat. That is that the kind of search that we are doing is a flat search, right? Now this L2 is distance, right? It tells you what kind of distance we are using. So there are multiple kinds of distances. The one that we are using is Euclidean distance, that is in straight line. Okay. There are I think it would be better if I give you one slide. So for ML specifically, that this thing matters a lot, right? Because require you to specify specifically what kind of distance or what kind of distance calculation methodology you want to use, and based on that their results do improve, right? Here Euclidean is a straight line distance, which is much easier for people to interpret or understand. But still there's a PPT which I would have from those days and I'll share it with you. It gives you all the kind of distances: Euclidean, Manhattan, vector, not vector, some sign, some researcher's name. So there are multiple kind of distances, but I think the Euclidean one is used the most for our use case at least. Okay. So this is how we are creating the index as of now. Now, if there would have been more, right, we would have taken a different, right? So let's see the other options that we have. So you see so many options do we, right? So HNSW, right? This creates a graph structure. So if you have a very large data set, you can use this one. Okay. And there is one more flat. Yes. So IVF flat. Okay. This, what it does, it divides vectors into clusters first and then only searches the nearby clusters, right? So like instead of searching every shop in Pune, right? You first go to the right neighborhood, and like you go to a mall and then start searching for that shop. So you concentrated there, much easier for you to find. And HNSW creates a graph. right? So with graph, it becomes much easier for it to be able to space through multiple sets of documents. Okay, but anyways, for our use case, let L2 is more than enough. Okay, but I would really want all of you to play with FAISS a little, right? And then move to a vector data, because it's like going step by step. If you don't know, if you directly go to a vector database, you might miss on a kind of learning, because later on, if you directly start working with a vector database, you will never find a need to go to FAISS. But from POC's perspective and interviews perspective, FAISS is needed. Okay, again, if all of you are not planning, right, FAISS is, you can skip it completely. Okay, all right. Now next is, once you have this, right, what we have to do is we have to keep adding the complete embeddings, as we said, right? You create it and then add all the embeddings, creates those embeddings. All right, then let's print the complete total, as well as, I would say, let's, why not directly get the dimensions here as well. Okay, so the number of embeddings it is created. All right, and its values. Okay, so we'll just give it a little space so we know where we are. See this request you are searching, just this one. You are sending unauthenticated request to HF hub. What is this HF?
Hugging
Hugging
Face.
Face.
Yes. How many of you have worked on any model with hugging face? None? I'm pretty sure you have. If not, then you're working for, the notebooks that I'm going to share with you. You'll be working with the hugging face from now onwards, right? Now, just like Git, okay, if you want to use it, you can use it via tokens with authentication. See, the problem that we'll face if we have to, work with it, or any libraries from Hugging Face, if you do not authenticate yourself and you work with larger request, it might reject it, or the speed would be much slower. Anyways, let's come to our problem. So FAISS index has 10 vectors, each of dimension 384. Okay, so as you can see, 0 to 9, we have in total 10, and each with 384 dimensions. Okay, now we have built it. Okay, now we have to, we said FAISS is used for what? Used for searching. Yes or no?
Yes.
We any database that you want to build, what do you want to build it for? To be able to retrieve information, right? Okay, so let's do this. Okay, let's specifically make a query to it. Okay, and then let's see kind of output would it be able to generate. Okay, so we'll go with query one. We have, I think, 4 topics, right? Yeah, food, cricket, tech, and travel. Let's go with food first. Okay, all right, so if we have to go with related query, so instead of Mumbai, let's say what is popular Indian street food. Now just let's check once we have not given similar answers, just to check is it good. So Mumbai biryani is a dumb cook, popular, and right. So we are using popular. So popular word is used. So let's try to make it a little hard for it, right? Let's hope that it would be able to understand from its dimensions that if I ask for best, I would mean something related to popular. Okay, so this would be a food related query. Okay, and how do we query it? Firstly, we have to encode this query as well. Yes or no? And if yes, why?
Yes.
Okay, why?
It can't search text versus number. Can only search number versus number.
Now, so when you do index search, it would take query vector and the value of k. Okay, and it returns 2 arrays, distances and indices. So that is how far each result from the query, and the position number of the nearest vector. All right, which are the 2 things which will be able to give it, says equal. Yes. Okay, can you tell me what is k equals to 3?
3 nearest vector
Nearest
related to the
vector, the
query.
positions of, yeah, the positions of nearest vectors. Okay, so now we can print. All right, and what else do we need to print? The results. For the result, we can do a for loop. Now we have to look only for 3. All right, then we have to look for distance. Yes, this is correct. Now what is this 0 and what is
Maybe the distance between the birds or what we are
The
searching for.
distance.
Distance from each
So,
third, first, second,
okay.
third position.
So basically, if I say this, okay, let's give you this, or am I incorrect? Distance of the ith, right? And what you're looking for? The result, right? So ith result from the query. So if I would be, how does range works? 1, 2, 3. So we'll compare 0. What is that 0?
Query.
All right. So query, then second, from then third. Okay. And the lower distance would mean what? More similarity, and 0 would mean identical. Okay. Okay. It has given the comment as well. So index of the I. All right. Lastly, we can print the result. Okay. Now someone explain me, why am I doing I plus 1 in result?
We give it 0 if you. It will start from 0, right? So.
I think we give
Index.
AS 3, so it will search for three word or query. That's why, but not sure.
Okay. So this I and I plus 1, right? So the only difference is this would mean to I, you'll get the result of what we are seeing numbered, right? Result 0, 1, 2. You'll get in this manner, if you do 1, 2, and 3, you'll get instead of like 0, 1, 2, you'll get 1, 2, 3, right? So there's nothing else. So it's just how we want to print it. Okay. But the important part, look at the three sentences and the query that we have. Was it able to capture the right one for us? What is the best Indian street food?
Yes.
Right? It was able to tell you Mumbai Vada Pav is the most popular street food, right? And we didn't give a word. All right. So the distance of this sentence was nearest to our encoding. Okay. Hence, if it would have been a real world application, we would have got this as an answer. Does it make sense?
Yes, sir.
Yes.
About it, because this is pretty much, this is a revelation for all of us, right? This is how actually an LLM works, how the embeddings are actually working for us, right? We're just looking at it, a much simpler version of it. Anyone unclear or confused about it? Okay, hopefully not. Okay, then let's take a few more queries, okay, and just cement that it is actually able to understand. So let's take query 2, sorry, query 2. Now, which topic should we take? What all topics we have? Food, cricket, tech, and travel. I like to travel, so I'll take travel. Is that okay?
Yeah.
Okay. We'll take something which is, sorry, we'll take something which is not related to, or which is different, at least in the keywords, from Wonders of the World, Kerala backwaters of a scenic houseboat. Okay. So what could be, would be confusing for it? What, or tell me some beautiful to visit in India. Okay. Again, we have to encode it, and again float 32 because its index expects it to be in float 32. K equals to 2, validate against 3 queries. Okay. Now, and the same for loop that was there. Okay. Okay. Now let's run this and see, would it still, because the sentence post are very different in keywords, right? What is your guess? Would it be able to find the right semantics or the nearest sentence? Okay, before that, let's us specify. So if my question is, tell me a beautiful place to visit in India, out of the two sentences that we have, right, the Taj Mahal, do you think is more near to our question?
Kerala one.
Taj Mahal.
Red bottom.
Okay, but which, so both feel, you all feel that Kerala backwaters is the most popular, right? So now it would depend
Popular is
on,
Taj Mahal.
okay. So now it would depend on what would it give more importance to, the word most with the beautiful, because most would mean we are looking at something that is rare. Then it would be 7 to beauty. Then that would be scenic houseboat, right? So let's see what, I mean, from its model, what has it learned and how it would go. Don't tell me that, no, no, okay, the last one, right? Beautiful place to visit in India. Okay. So if you look at it, the distance of these two, 0.19 and 0.26. One reason is it would know that Taj Mahal is in India. That is one. Okay. But because places and everything, it would have realized 7 wonders of the brain, right? This is all very context dependent of how it would have interpret from embeddings, right? Ideally, these both could have been true. But look at the funny part. The third one, just because it mentions the word Mumbai, is distance wise not very far from Kerala back, right? But it will still have found out that these two are the real, or one of these two would be the right answer. But if you're using a smaller model, there's a possibility that its embedding, hence its knowledge, is limited, right? And if we would have taken only k equals to 2, the third one wouldn't have come in picture at all. Okay. Let's take one last query, right? So let's do one more query, and obviously we'll take third topic. Let's look at what all. Okay. So last one is, so this would be, because it just had one example, right? So I think would be very hard. All right. So we'll ask a question in that regard. Okay. So think of a query that is related to our question, but keyword wise, you know, very far. This is the actual sentence, right? We should not take this sentence. We should take, how is it hard to top G colleges in India? So keyword wise, this is very different, right? Let's look at it. We don't have anything that is similar, right? So this does, right? So this is very different. Okay. Again, now you remind me, what is the next step?
Embed.
You have your query. What do you need to do next?
Embed. Embed the query.
Okay, so first we have to encode it or embed it, right? So, okay, what is next? You have embedded the query.
Search. You have to search it.
How did we do it?
Index.search with the query and the key value.
Okay. After this, the same loop again. All right. Exact same. Nothing changes because we are just querying. Okay. Now, because there is no other of this topic, right? Engineering college, so I'm pretty sure it would be able to find the right one. But still, let's see how similar does it found, right? And for the, because we have taken top or k equals to 3, for the ones it finds, the other ones how far, right? I am not sure it is running or not at this point. Now it is. Okay. Is it able to find? Also, we didn't print the query, right? Yeah, we didn't print the query, but that's okay. So IIT entrance exam is one of the toughest in India. Our query was, is it hard to get into top engineering colleges in India? So it got 0.90, which is the nearest distance. And next was TCS and Infosys are India's largest IT companies. And what do you think? Why would it would have gone to this one, the next?
The keyword, like the word top thing in India.
Uh, See, because it learns in in from the data that internet or in engineering college and placements, those words would have been used regularly with TCS and Infosys, right? And after this, semantically, it would have realized this would be the nearest point. Okay. Again, this the understanding of it is a black box to us, but we know that it's through embeddings that it understands the semantics. Okay. So with that, that is how FAISS works, right? Do play with it. I'll share you three or maybe four notebooks, right, with code snippets, more detailed ones than what we perform on. The next two, which we cannot complete today, because again, I don't want to rush through it. Chroma DB or any vector database is a very important question in interviews, so we should go slow on it. Okay. So in the next session, we'll start with these Chroma DB and semantic search, and only then we'll move towards RAG.